Hello everyone, I'm Takeru Koyama. We are Satori Shiodani, Dogo Sakamoto, Yuki Watanabe, Takeru Koyama, Junta Yoshimoto. Today we want to talk about nuclear energy and nuclear development in Vietnam. These are contents. First, what is nuclear energy? Uranium atoms are split inside a reactor. The heat produces boiling water, creating steam that turns a turbine to generate electricity. This is the process of splits a large atom to produce energy. It is used to generate electricity in nuclear power plants. According to the latest cost assessment by Japan's Ministry of Economy, Trade and Industry, the estimated electricity generation costs are approximately nuclear power and 12.6 yen per kilowatt hour or higher, LNG fired power and 19.1 yen per kilowatt hour. Coal-fired power, 24.8 yen per kilowatt hour. So why nuclear power can be cost competitive? Uranium fuel accounts for only a small portion of total generation costs. Nuclear power plants can operate for 40 to 60 years or longer, allowing the high construction cost to be received over a long operating period. Fuel prices are relatively stable compared with fuel and fossil fuels. The overall cost of nuclear power depends on whether the following expenses included: decommissioning cost, radioactive waste management and disposal, safety enhancement measures, accident risk, and compensation cost. And similarly, the cost of thermal power depends on whether external costs, such as greenhouse gas emissions, climate change impacts, and public health effects are taken into account. Therefore, it is difficult to conclude that nuclear power is always cheaper than thermal power, or vice versa. The result depends on the assumption and cost components included in the analysis. This is the disadvantage. Radioactive waste is difficult to manage. Nuclear accident can cause serious damage. Decommissioning nuclear power plants require a lot of time and money. Second, a global trend in nuclear energy. Current states of nuclear power. Nuclear power is an important source of electricity. It produces little carbon dioxide, but it has problems such as high cost, radioactive waste, and safety concerns. Some countries are using more nuclear power, while countries are using less. For example, China, India, Japan, Russia, and the UK are expanding nuclear power. On the other hand, Germany, Spain, Switzerland, and Belgium are reducing or phasing out nuclear power. These are major nuclear power countries: Today, I will be giving a presentation about Japan and Russia, countries with ties to Vietnam. Japan has strengthened nuclear safety since the Fukushima Daiichi accident. It is restarting some nuclear power plants while expanding renewable energy. Russia generates about 20% of its electricity from nuclear power. It also exports nuclear technology and develops advanced reactors, including fast reactors. The role of nuclear energy in achieving carbon neutral. Carbon neutral means achieving an equal balanced carbon dioxide emission and absorption. Nuclear energy produces very little carbon dioxide. It helps reduce greenhouse gas emission and provides stable electricity. Therefore, many countries use nuclear energy to achieve carbon neutrality.
Next, history of nuclear technology and nuclear power development in Vietnam. The Darat Research Reactor. This is Vietnam's foundational nuclear facility. Upgrade with Soviet help in 1984. Now using low enriched uranium to produce chemical radioisotopes and train scientists. The Incheon Nuclear Power Project, a revived mega project split into two sites. Incheon 1, Russia's VVER-1200 reactors. Incheon 2, exploring global tech like SMRs. Current nuclear policy in Vietnam. Driven by net zero goals, Vietnam implemented new atomic energy law in 2026, prioritizing strict safety, SMR adoption, and massive workforce training. Next, why was Incheon selected as the site for Vietnam's nuclear power project? It is near the sea, so it is easy to get a lot of cooling water. The place is dry, we can get easy cool water. Energy demand. Vietnam's economy has been growing quickly, so more electricity is needed. The government also wanted to reduce its dependence on coal and natural gas. Power grid and infrastructure. Vietnam was already planning to expand its power grid and other infrastructure. This also made Incheon a good place. The country is working to strengthen 500 kilovolts and 220 kilovolt transmission lines connecting the north, central, and south, eliminate output curtailment and promote investment so international corruption and new government decrees. Government policy. The government also had a nuclear power development plan for 2030. Incheon was chosen as the plant site. Last, relationship with regional development. I think the project could improve roads and other infrastructure. It may also make the area a better place for people to live.
Okay, good morning, everyone. Good afternoon, everyone. On the behalf of our team, I would like to continue the presentation of our group. And for our topic now, we'll focus on safety standards and future outlook of nuclear safety, of the nuclear power. And now a little bit of introduction. A comprehensive research and discussion document on nuclear safety practical lessons from Japan's Fukushima disaster, a contextual comparison between Vietnam and Japan, and the vision for developing next generation nuclear technologies.
Indeed, it is a privilege to present to such an esteemed audience. To guide you through our topic today, we will explore three key sections. First, nuclear safety standards and mechanisms through the lessons of Fukushima. Second, a comparative analysis of contexts and policies between Vietnam and Japan. And finally, the development trends of next generation nuclear technology.
Now, to begin with, to truly understand nuclear safety, we must look back at the Fukushima Daiichi disaster that occurred in March 2011 in Japan. We got a little clip here. You can see here initially a 9.5 magnitude earthquake successfully triggered the automatic reactor shutdown system. However, shortly after, the subsequent 14 to 15 years tsunami oversaw the 5% real sea. Completely flooding the planet. And as a result, a station blackout occurred. The cooling systems failed, causing temperatures to rise rapidly and leading to core meltdown in units 1, 2, and 3. Furthermore, high temperature chemical reactions generated large amounts of hydrogen gas, ultimately resulting in structural explosions and release of radioactive materials into the environment. Okay, so now, a common question often arises: why wasn't the Fukushima plant designed to withstand such a massive tsunami? Was it a flaw in the original American design or simply an unpredictable application? The short answer is neither. The root cause lies in institutional complacency and the failure to act on scientific warnings. When the Tokyo electric power computer company built the plant in the 1960s, it calculated its maximum tsunami height based on limited historical data, such as 3.1 meters, later adjusting their seawall to 5.7 meters. However, as geological science advanced, warning signs emerged. In fact, as early as 2008, internal engineering reports explicitly warned the company of potential waves exceeding 15 meters, almost identical to the 14 to 15 meter tsunami that struck in 2011. Regrettably, due to a misplaced faith in their existing engineering, a mindset known in Japan as Anzen Shinwa or the safety myth, management delayed necessary safety upgrades and seawall enhancements. Therefore, as the Japanese National Diet officially concluded in their investigation, Fukushima was ultimately a man-made disaster. A tragic reminder that technology safety is only as good as the human willingness to adapt to new scientific realities.
Fortunately, thanks to these costly lessons, the global safety framework was heavily reformed. Today, plants are equipped with mobile pump systems, flex subjected to rigorous stress tests, and overseen by independent regulatory bodies such as the Nuclear Regulation Authority (NRA) in Japan.
Okay, we can see a brief here about the human social impact, the mass evacuation, indirect casualties, and also the psychological trauma. Yep. The total estimated cost is about $200 billion. It's a massive economic loss. And also about the environmental consequences, radioactive contamination, and extensive exclusion zones were created around the plant. 26. And also shift in global energy policy. From 2011, many things happened like declining trust, energy strategy overhauls in 2026. Japan shut down all its nuclear reactors. Immediately following the disaster, many countries conducted stress tests on their own plants. Okay, so this brings us to an important question. How is a modern nuclear plant protected? Fundamentally, the safety philosophy relies on defense in-depth concentric barriers. First, you can see the nuclear safety systems. The first thing is physical barriers, consisting of 4 robust layers: ceramic, fuel pellets, zirconium, alloy coating, heavy steel reactive pressure vessels, and reinforced concrete cosmetic buildings. To illustrate, you can think of this like luxury cars, protective frames, safeguarding its passengers. The second one is active safety systems, emergency water pumping mechanisms that require external power. And the last one will be passive safety system. Most importantly, this is a breakthrough in modern technology that automatically cools the reactor using natural laws, such as gravity or thermal convection, without requiring electricity or human intervention.
In addition to reactor design, comprehensive safety also involves 3 crucial aspects. The first one is radiation protection. We strictly apply the Balara principle, which stands for as low as reasonably achievable, through 3 key factors. Time, which is minimizing exposure time; distance, intensity decreases with the inverse square of distance; and shielding, using lead, heavy concrete, or waterproof. Next is waste management. High-level waste is first put in storage pools for 3 to 5 years, then transferred to durable steel and concrete dry cast, and ultimately isolated permanently in deep geological repositories such as the Onkalo project in Finland. And finally, the nuclear security. More security is strictly monitored by the International Atomic Energy Agency to prevent non-proliferation risk. Plant structures are built to withstand commercial aircraft impacts, and control systems are air-gapped from the internet to prevent cyber attack. On top of all these measures, establishing emergency planning zones, stockpiling potassium iodide tablets to protect the thyroid, and conducting regular drills are mandatory to proactively respond to any situation. Now, moving on to the second part of our presentation, let's compare the nuclear landscapes of Vietnam and Japan. The first aspect is energy policy. So, Japan are restarting safe reactors to achieve net zero. Meanwhile, Vietnam suspended the Newton project in 2016, currently focusing on renewable energy and liquefied natural gas, but reconsidering nuclear in the long term. Turning to the public opinion, Japanese citizens are highly cautious post-Fukushima with strong opposition. However, in Vietnam, there are no historical prejudice. Main concerns are safety, cost, and avoiding power shortage. Lastly, the legal framework in Japan is extremely strict with an independent nuclear regulation agency. On the other hand, currently Vietnam's legal framework is at a operational level, and the Vietnam Agency for Radiation and Nuclear Safety needs comprehensive upgrades.
Okay, so looking at this comparison, what can these two nations learn from each other? In Vietnam, independent regulation, safety oversight must be completely separated from economic ministries to prevent conflicts of interest. Strong safety culture, of course. Safe operations rely on strict human discipline and protocol adherence, not just advanced hardware. Lastly, with extreme scenario planning, anticipate compound disasters such as extreme climate events instead of relying solely on historical data. Japan, I think we think that micro strategic flexibility, halting the Ningbo project in 2016 demonstrated this decisive risk management and avoidance of the sunk cost fallacy. Also, rapid renewable integration. Vietnam's booming solar and wind sectors offer a practical case study for Japan on diversifying clean energy sources. And now, moving to the last part about the future development of nuclear energy. Okay, moving on to the next slide. Let's take a closer look at the global energy share comparison based on recent 2024 to 2025 data. We can see here that nuclear energy currently accounts for 9% of the total world share. And also hydrogen represents 14%, while wind and solar combined make up to 16%. The remaining 61% belongs to other traditional energy sources. Crucially, why a 9% share of nuclear energy may seem modest at first glance, it serves as a remarkably stable and carbon-free baseline in today's global energy mix, acting as a crucial foundation as we transition toward cleaner technologies.
Turning to the next section, where is the future of nuclear energy headed? Today, we are entering an exciting era of groundbreaking technologies. First one is small modular reactors, SMRs, having a capacity under 100 megawatts. SMRs are mass manufactured in factories and transported as complete modules, which significantly reduces construction time and cost. Above all, they maximize passive safety systems, cooling naturally without power or action. Next is generation 4 reactors. These reactors replace water coolants with liquid metals such as sodium or lead, molten salt, or high temperature helium gas. Operating at a low pressure eliminates steam explosion risks, achieve high thermal efficiency, and can even recycle old nuclear waste as fuel.
Looking even further ahead, nuclear fusion is considered the holy grail of clean energy, mimicking the reaction that powers the sun. This technology uses virtually unlimited fuel from seawater, produces no long-lived radioactive waste, and carries zero risk of meltdown. Currently, two international mega projects like ITER are turning this vision into reality. The next one will be peak hydrogen production. In addition, using heat and electricity from advanced reactors allows us to perform high temperature water electrolysis, producing zero carbon fuel, ideal for heavy industry and transportation.
The final part is the backbone of the energy grid. Ultimately, in the future energy mix, nuclear power serves as a stable 24/7 baseload power source. It perfectly complements the intermittent nature of weather-dependent wind and solar power, thereby ensuring national energy security and keeping overall infrastructure running without interruption.
To summarize, nuclear power is undergoing a major transformation, from strict lessons learned in the past to advanced technological breakthroughs for the future.
In conclusion, it remains a vital key in helping the world secure energy needs while reaching the global goal of net zero emissions. Thank you, distinguished professors and students, for your kind attention. We are now open for any questions or discussions.